Hi everyone, in this video we are going to discuss about exponential equations. Exponential equations are those kind of equations where the variable is in the exponent. Now as you can see on the screen, I have the first form of exponential equation where we say that if a to the power x is equal to a to the power m, then we can safely say that x will be equal to m. However, there is one condition. Condition is that a cannot be 0, a cannot be positive 1 or negative 1. Now why a cannot be 0, positive 1 or negative 1, I will explain in a while. Now assuming that a is not equal to 0 and not equal to 1 or negative 1, then how can we prove that a to the power x equals a to the power m would mean that x equals m? Well, let's try to do the proof. So the proof would be very easy right here. So let's say, suppose we have a to the power x is equal to a to the power m. Now from here, if we divide both sides by a to the power m, then what do we get? Well, we'll get a to the power x divided by a to the power m is equal to 1 on the right hand side. And we have assumed that a is not equal to 0. So dividing both sides by a to the power m should be fine, right? Because a is not equal to 0. So a to the power m definitely not equal to 0. So division by a to the power m should be alright. And that's exactly what I have done. Now from here, can we say that okay, so using the properties of exponent, can we say that okay, on the left hand side then we must have a to the power x minus m, the exponent will become x minus m, and then on the right hand side we have 1. Can we write that as maybe a to the power 0, because any non-zero number to the power 0 gives us 1. And then now you see that we have same base on both sides and the powers are different. Well, the powers look different, but because the base is same and it is an equation, we can say that the powers must be equal. So from here we can say that x minus m must be equal to 0, and from here we can say that x must be equal to m, and that's exactly what we wanted to prove, and that is what we have it right here, that x must be equal to m, and here also we have proved the same thing, that is x is equal to m. Now what are the problems with 0, 1 and negative 1? Let's quickly talk about that. Say suppose if we take 0, then you see, can I say that 0 to the power 5 is equal to 0 to the power 10? Of course we can say that. Why? Because 0 to the power 5 is 0, 0 to the power 10 is also 0. So they both are 0. Now does this mean that 5 is equal to 10? Well, actually not, right? We all know that 5 is not equal to 10. So that is not true. So that means if we use 0 for the value of a, then this theory will not be true, right? So that is why we cannot have 0 as the value of a in this particular theory, right? So similarly, let's go with another number. Let's say 1, right? So suppose, can we say that 1 to the power 5 is equal to 1 to the power 10? Yes, of course we can say that, because 1 to the power 5 is equal to 1. 1 to the power 10 is also equal to 1. So they both are equal, right? But from here, can we say that, hey, 5 is equal to 10? Definitely not. We know that 5 is not equal to 10. So that is why we have to avoid 0 and we have to avoid 1 also. Now how about a negative 1? Well, let's try that. So let's say, suppose we have negative 1 squared, and then also we have negative 1 to the power 4. Now would they be equal? Yes, of course they will be equal. Why? Because negative 1 squared would be positive 1. Negative 1 to the power 4 will also give us positive 1. They both are equal. But does this mean that 2 is equal to 4? Absolutely not. 2 is not equal to 4. So we cannot use the negative 1 either. So that means we have to avoid the 0. I am doing a red underline way at the top right corner there, and also you have to avoid the positive 1 and negative 1. So those are the three numbers that are prohibited for the value of a. If a is any number other than 0, positive 1 or negative 1, then we can say that a to the power x equals a to the power m would mean x equals m. Now let's take an example. Suppose we have an example like this, 2 to the power 4x is equal to 16 squared, right? Now somehow you want to bring it into the same base on both sides. So on the left hand side we have a base of 2, so we are going to keep that as is. So let's still continue to say, okay, left hand side is 2 to the power 4x. But how about the right hand side? Well, 16 is actually 2 to the power 4. So we can say this must be equal to 2 to the power 4 whole squared, which is obviously equal to 2 to the power 8. Because if we have a to the power m whole to the power n, then it becomes a to the power m times n. Here also it became 2 to the power 4 times 2, which is 8, 2 to the power 8. So from here, now you see that we have an equation, we have an exponential equation here where 2 to the power 4x is equal to 2 to the power 8. So let me again write it down here. So 2 to the power 4x is now looking like equal to 2 to the power 8. And because 2 is not 0, 2 is not 1, 2 is not negative 1 either. So from here we can say that okay, then 4x must be equal to 8. The exponents must be equal. And from here we can say okay, then x must be equal to 2. That would be 8 divided by 4, that would be 2. And we have found the solution of this exponential equation. Now let's talk about the second form of exponential equation. The second form of exponential equation is like this. Say if we have a to the power m is equal to b to the power m, where a and b are not equal, they are different numbers, then we can say that either a is equal to b if m is not equal to 0. So let me quickly put this condition right there, that when m is not equal to 0, if m is not equal to 0, then definitely a will be equal to b. Now if a and b are not equal, then obviously m has to be 0, then only this equation is possible, right? Now let's assume that m is not equal to 0, right? So then how can we prove it? So we have a to the power m is equal to b to the power m. Now from here, if we take mth root on both sides, then what do we get? Well, we can say from here that if we take mth root on both sides, then again both sides would be equal. So now I'm going to do mth root of a to the power m, and then on the right hand side also I'm going to do the same mth root of b to the power m, and from here we can write it like this. Okay, then a to the power m whole power 1 by m, that is the mth root, would be equal to b to the power m whole power 1 by m, and from here then you see that it will be a to the power m times 1 by m is equal to b to the power again m times 1 by m. So from here we can say okay, then a to the power 1 is equal to b to the power 1, and from here we can say okay, then a must be equal to b when m is not equal to 0. So we have proved that yes, when m is not equal to 0, a is equal to b. And if a is not equal to b, then can we say it like this? Let's say suppose we have a to the power m is equal to b to the power m. Now if we divide both sides by b to the power m, then what we'll get? We'll get a to the power m over b to the power m is equal to 1, and from here we can say okay, the left hand side is a over b whole to the power m is equal to 1. Now can we write it like this? Left hand side is a over b whole to the power m and right hand side is 1. Can we write that as a over b to the power 0? So I'm going to write it like this, because any non-zero number to the power 0 always gives us 1. So from here can we say that okay, because we have the same base on both sides, then m must be equal to 0. So when a and b are not equal, then we have proved that m must be equal to 0. So those are the two possibilities, right? Either m is equal to 0 or a is equal to b. If we have a to the power m is equal to b to the power m, then we can say that either a is equal to b or m is equal to 0. Let's take an example. So suppose we have an example like this. So we have an example like this: 2x plus 3 whole squared is equal to x to the power 4. Right? Now can we write it like this? We want to have the same exponent then, right? Let's try to express it in the same exponent form, because the base is completely different. On the left hand side we have 2 times x plus 3, on the right hand side we have just x, so it's difficult to make the base equal. So let's try to make the exponent equal and see what happens. So on the left hand side we are going to keep the same thing, 2 times x plus 3 whole squared is equal to, now x to the power 4, can we write it like x squared whole squared? Yes, we can write it like that, right? So then now you see, because you have the same power on both sides, meaning same exponent on both sides, then the base must be equal. So then from here we can say okay, then 2 times x plus 3 must be equal to x squared, and now it's a nice quadratic. So from here we can quickly solve the quadratic. So it would be x squared minus 2 times x and minus 3 is equal to 0, and now we can write it like this: x squared minus 3 times x plus x minus 3 is equal to 0. I'm just trying to factorize it. So then from here we can say okay, x times x minus 3 and then positive 1 times x minus 3, all of that is equal to 0. And then what are our two factors? Well, x minus 3 is definitely a factor, and then also we have x plus 1 as another factor. this product is equal to 0. So from here we can say that if x minus 3 is equal to 0, that is one situation, or we can say that x plus 1 is equal to 0. So from here we are going to get two values. So x is equal to 3, that is one possibility, or x is equal to -1. And that is our solution. So whenever you have an exponential equation, try to see if the base can be made equal or if the exponent can be made equal. If you can make the base equal, then the exponent could be different looking, but then you can say, hey, because the base is equal, the exponents must be equal. You can also try to make the exponent equal, then you can say, hey, because the exponents are equal, then the base must be equal. So those are the two different forms that we have discussed so far, right? Next, we are going to talk about the third form of exponential equation. The third form of exponential equation is like this. Say suppose if we have a to the power some function of x is equal to 1 and a is positive and a is not equal to 1, then we can say that that function of x must be equal to 0. Let's take an example. Say suppose we have 3 to the power x squared minus 3x plus 2 is equal to 1. Now you see this is an exponential equation where the variable is in the exponent, and here what do we say? The theory says that hey, if your a is positive and a is not equal to 1, in this case a is actually 3, number 3 right here, so then we can say that the exponent, which is looking like a function of x, that exponent is equal to 0. So from here we can say, okay, if this is the case, then we can safely say that our exponent, which is x squared minus 3 times x plus 2, must be equal to 0. That comes straight from the theory, right? And then if we try to solve it, this will become what? This will become x squared minus 2 times x minus x and plus 2 is equal to 0. I'm just trying to factorize it, and from here we can say, okay, then x times x minus 2 and then minus 1 times x minus 2 is equal to 0, and from here we can say, okay, then x minus 2 times x minus 1 must be equal to 0. From here we can say, okay, then x minus 2 is equal to 0 or x minus 1 is equal to 0, and from here we can say, okay, then x must be equal to 2 or 1. And that is our solution. So for this equation, the solution is that x is equal to 2 or x is equal to 1. So if you use a value of 2, then also it will be true. If you use a value of 1, then also it will be true. Next, we are going to talk about the fourth form of exponential equation. The fourth form of exponential equation says that if we have a function of a to the power x where a is a constant, right? It's a non-zero constant. So if you have a function of a to the power x and that function is equal to 0, then we can write it as a function of u equals 0 where u is actually a to the power x. So in place of a to the power x, if we substitute that with u, then we can say, okay, then f of u will also be equal to 0. So that's a very simple case here, right? Now let's take an example and we'll learn it through an example. So suppose we have an equation like this where 3 to the power 2x minus 8 times 3 to the power x minus 9 is equal to 0. Now you see, looks like we have 3 to the power x as the a to the power x here in this equation, right? So from here, let's try to isolate the 3 to the power x. So can we do it like this? So from here we can say, okay, the first term here, which is 3 to the power 2x, can we write it as 3 to the power x whole squared? That is same as 3 to the power 2x. And then in the second term, we have 8 times 3 to the power x, and then we have negative 9 is equal to 0. And from here what can we say? Well, let's substitute this 3 to the power x with u. So let's assume that 3 to the power x is equal to u. With that assumption, I'm just going to substitute in this equation wherever we have 3 to the power x, I'm going to use u. So now can we say that this must be u square minus 8 times u minus 9 is equal to 0, and from here let's try to factorize it. So this would be u squared minus 9u plus u minus 9 is equal to 0, and from here we can say that, okay, take u as a common factor, then we have u minus 9 and then plus 1 times u minus 9, and all of that is equal to 0. And then from here we get that u minus 9 as a common factor times u plus 1 is equal to 0, and from here what do we get? Well, then u minus 9 must be equal to 0 or u plus 1 must be equal to 0. So then from here what do we get? We get u must be equal to 9 or u must be equal to -1. And now we have to be very careful because you see what is our u? u is actually 3 to the power x, meaning 3 to the power something that is equal to u. So can that ever be a negative number? I mean, positive 3 with an exponent of anything, can that ever be a negative number? The answer is no, it can never be a negative number. So we really cannot take the value of negative 1. We have to discard this value. This value cannot be taken for u because u is actually positive 3 to the power something, and that can never be equal to a negative value, right? So this must be discarded. I'm putting a cross sign there. So what we can take, this is the only value we can take, the u equals 9. So from here, can we say that, okay, therefore u must be equal to 9. We cannot take the negative value, right? So now if u is equal to 9, so from here, can we say that, okay, so now what is our u? Well, u is actually 3 to the power x. So 3 to the power x is equal to 9. So can we write 9 as 3 squared? Now you see, we clearly see that 3 to the power x is equal to 3 squared. So now we have the same base, the exponent must be equal. Because the bases are same, the exponents must be equal. So from here we can say that x must be equal to 2. And that is our solution for this equation. Next we are going to discuss the fifth form of exponential equations. The fifth form of exponential equation says that if we have an equation like alpha times a to the power f of x plus beta times b to the power f of x plus gamma times c to the power f of x is equal to 0, and also b squared is equal to a times c, then the first equation is equivalent to alpha times u squared plus beta times u plus gamma, where u is equal to a over b whole to the power f of x. It looks kind of crazy, right? It looks like a lot, but actually it's very simple. If you assume that alpha is a number and a is another number, similarly beta is a number and b is another number and gamma is another number and c is another number, those are all different constants, right? And then if we have an equation like this, alpha times a to the power some function of x plus beta times b to the power the same function of x, and then gamma times c to the power the same function of x is equal to 0, and also if we see that b squared is equal to a times c, then we can rewrite that equation in the form of alpha times u squared plus beta times u plus gamma is equal to 0, right? So let's take an example. So suppose we have an example which is 27 times 2 to the power x minus 12 times 6 to the power x plus 18 to the power x is equal to 0. So here let's try to understand what are alpha, beta and gamma values, and also what are the a, b and c's here, right? So let's make some quick notes here. So here you see this is our alpha, which is 27. So I'm going to make a note like this. So this is our alpha. And then 2 to the power x, this 2 right here, this 2 is actually a, and then x is the f of x. So this x right here, we can say, okay, this is our f of x, some function of x, and x is also a function of x, right? And then what is our beta? Well, beta is actually the negative 12 right here. So the negative 12 is actually equivalent to the beta. And what is b? Well, b is actually equal to 6 right here. So this is our b. And then what is gamma? Well, gamma is actually 1 because there is no other coefficient. It's 18 to the power x. So we can say, okay, then gamma is equal to 1. So how do I show that? Well, here I would say gamma is equal to 1 and then 18 is equal to c. Because you see the 2 also has the power of x, 6 also has the power of x, and 18 also has the power of x. They all have the same exponent, and which looks like a function of x, right? So all of them are f of x right here. This is also f of x, the same f of x, which is just x, and here this is also f of x. So now this example equation kind of looking like our equation in the theory there, right? So now from here what can we do? And let's also double check and see if b squared is equal to ac. Now what is b? Well, b is equal to 6. So can we say, okay, 6 squared would be 36, right? So b squared, we are going to now check b squared equals ac, whether that is the fact, right? So in this case you see 6 squared. So here we can say 6 squared is equal to 36, which can also be written as 2 times 18, and you see the 18 right here and the 2 right here. 2 is the a and 18 is the c. So a times c would be 2 times 18, which is equal to 36, and that 36 is actually equal to square of 6, which is the b right here, right? So we also see that b squared is equal to a times c. So from here we can say, okay, then b squared is also equal to a times c. That means our original equation can be converted into the other form. Now let's see how we can convert that, right? Yes, it can be converted, but I'm going to show you right here how to do it. So now from here, let's do this little math right here. So from here we can say, okay, we are going to now divide both sides by 6 to the power x. So let's divide both sides by 6 to the power x and see what happens. So here we'll have 27 times 2 to the power x divided by 6 to the power x minus 12 times 6 to the power x divided by 6 to the power x plus 18 to the power x divided by 6 to the power x. All of that is equal to 0 divided by 6 to the power x. That will obviously be equal to 0. So I'm just simply writing 0 right here. And then from here we can say that, okay, this must be 27 times 2 by 6 or 2 over 6 whole to the power x minus 12 times 6 to the power x divided by 6 to the power x, that will be 1. So this is 12 times 1 plus here we have 18 divided by 6 whole to the power x is equal to 0. And now let's try to simplify a little more. From here we can say that, okay, this must be equal to 27 times 2 and 6. So that would be 1 over 3. 1/3, that would be 1 over 3 whole to the power x, because 2 is a common factor between 2 and 6. So if we reduce that, this comes to 1 over 3, and then minus 12. So 12 times 1 is actually 12, and plus this one will be 3, right? Because 6 3s are 18. So that would be 3 to the power x, and can we write it as 1 over, then 1 over 3 to the power x. So 18 over 6 whole to the power x can be written as 1 over 1/3 whole to the power x. Now as you can see that what was our a? Well, our a is actually 2 and b is actually 6. So now we are almost in a form like this, that if we say, so what would be a by b then? Can we write it like this right here on the side? I am going to say, okay, then a divided by b is actually 2 over 6, which is actually 1/3. So now you see, wherever we have 1/3 or 1 over 3 whole to the power x, that is actually in the form of a over b whole to the power x, and we're going to replace that with a u. So let's try to replace that with a u, right? So now what I'm going to do, I'm going to say, okay, then this must be equal to 27 times u minus 12 plus 1 over u. All of that is equal to 0. Now let's multiply both sides by u. So this will become 27u squared, because we already have a 27u and we are multiplying by u on both sides. So this will become 27u squared minus 12u plus 1 is equal to 0. And as you can see, we have been able to convert the equation into the form that our theory was suggesting. Our theory was suggesting that it can be converted into the alpha times u squared plus beta times u plus gamma is equal to 0, where alpha is 27, beta is negative 12, and gamma is 1. So you see, we have exactly what the theory suggested, that now we have an equivalent equation which is 27 times u squared minus 12 times u plus 1. So 27 is the alpha, negative 12 is the beta, and 1 is the gamma. So we have alpha times u squared plus beta times u plus gamma is equal to 0, right? And then from here we can easily solve it. So let's try to factorize this equation here. This is a quadratic, so this would be 27 times u squared. So you can write it as negative 9u and negative 3u plus 1 is equal to 0. And then between the first two terms we can have 9u as a common factor here. So let's say 9 times u, then we have 3 times u minus 1, and then negative 1 times 3 times u minus 1. All of that is equal to 0. And then from here we're going to say, okay, then 3 times u minus 1, that is a common factor, and then we are going to be left with 9 times u minus 1. All of that is equal to 0. And from here we can say, okay, then 3 times u minus 1 must be equal to 0, or 9 times u minus 1 must be equal to 0. And then from here we are going to get two solutions. So 3 times u is equal to 1, or 9 times u is equal to 1. And then from here we can say, okay, then u is equal to 1/3 or u is equal to 1/9. So we have two possible values of u. And then what is u actually? Well, in this case u is actually 1/3 to the power x. So now we can say, okay, so 1/3 to the power x, 1/3 to the power x, I'm just using the value of u, right? U is actually 1/3 to the power x. You can see right here, I'm doing a yellow underline there. So 1/3 to the power x is equal to u. So here I can say that, okay, then u is equal to 1/3, or again I can say this is our u is equal to 1/9. Now from here, let's try to solve for x. So from here we can say, okay, can we write it as 1/3 to the power x as 1/3, no power means power 1, right? And similarly on the other side also we can say, okay, 1/3 to the power x is 1/9. Can we write it as 1/3 whole square? So from here we are getting two possible values. You see, we have the same base, that means exponents must be equal. So you can say, okay, then x must be equal to 1 or x must be equal to 2. So those are the two solutions for this equation. I hope everything made sense so far. And finally, we are going to talk about the sixth form of exponential equation, and that's an easy one. We'll quickly talk about it. The sixth form of exponential equation is like this. So suppose we have an equation which is like a to the power some function of x plus b to the power the same function of x is equal to c, where a, b and c some non-zero constant. And also a squared plus b squared is equal to c. So the value of a, b and c are such that a squared plus b squared is equal to c. Then we can safely say that f of x must be equal to 2. There is no other possible solution. This is the only solution here. So suppose, let's take an example. Suppose we are given an equation like this: 2 to the power x minus 2 plus 3 to the power x minus 2 is equal to 13. And here you see a is 2. This 2 is actually equivalent to the a as in the theory. So this is our a, and here this is our b, and this is our c right here. So 13 is the c. Now you see, if we do a squared plus b squared, let's see what happens. So a squared plus b squared is actually equal to 2 squared plus 3 squared, which is equal to 4 plus 9, which is equal to 13, and that is actually equal to c. So now you see that yes, in this particular example we have a squared plus b squared is equal to c. Then definitely the function of x which is in the exponent, that must be equal to 2. So from here we can say that therefore the exponent which is x minus 2, that is the f of x which is in the exponent, that must be equal to 2. And from here we can say, okay, then definitely x must be equal to 4. And that is the only situation when this is possible, and that is the only solution that we can get. This brings us to the end of this video. Hope everything made sense. Thank you for watching. See you in the next video.